Okay, section 7.6 part 2. So Bayes' theorem basically says, so let A1, A2, all the way through A sub I be partitions of a sample space. So remember the Venn diagrams, they're individual partitions within that sample space. They are mutually exclusive. Such that the probability of A sub I is not 0 is between 1 and n. And E be an event of the experiment such that the probability of E is also not equal to 0. Then the a posteriori probability of A given E can be found by, and here's our formula. It's a really ugly looking formula. So first we're going to see it in words, then you'll see it as a formula, and then we're going to use it and show you how much easier it is to use than to say. So the probability of A partition I, so one of the partitions of A, given that E has already occurred. So basically you take the product of the probabilities along the branch that starts with A and ends at E. So starts at A and ends at E, right? Over the sum of the products of the probabilities along every branch that ends at E. So that means that you multiply across all of them and add them down to get the denominator in this. So the formula says the probability of A sub I given E is equal to the intersection, which we already know. This is the intersection from our previous work, all over on the bottom, the probability of E. And because E occurs in multiple spots, you have to multiply across and add down. So example 2 gives us a tree, except for it's an incomplete tree. So the accompanying diagram represents a 2-stage experiment. Here's the first stage, here's the second stage. The 3 events A, B, and C form a partition of the sample space. Complete the information on the diagram and use it to find the probability of B given D. So we're looking for the probability of B given D. And again, that's we're looking for the left given the right. And that's what they call posteriori. Well, let's fill in the missing blanks first. So let's do the easy ones. If this is 1/5, these two have to add to 1. This is 4/5. If this is 2/5, this needs to be 3/5, adding to 1. If this is 1/4, then this is 3/4, again adding to 1. Over here we have 1/4 and 1/3. I need them to have a common denominator to do this. So this would be 4/12. This would be 3/12. 3 goes into 12 4 times. 4 times 1 is 4. 4 goes into 12 3 times. 3 times 1 is 3. That's 7/12. We're missing 5/12. So there's the complete tree. Okay, well now we're going to use it and show you how easy this formula is. So to find the probability of B given D, first of all, we need the intersection. According to the formula, that's the probability of B intersect D. So that represents the branch that starts at B and ends at D. So for us, starts at B, ends at D. So that would be 5/12 times 3/5. Notice that these guys are going to cancel. It's fluke. That's not always going to happen. Over, according to the formula, the probability of D. Because D occurs here, here, and here, we need to sum the products. So we're going to multiply across along each branch that ends at D in this case. So our first branch would be 1/4 times 1/5. Plus, there's the first branching, the second branching, which is the 5/12 and the 3/5. Plus the last branching, which is 1/3 times 3/4. And there it is. And that's Bayes' theorem. So this is what Bayes' theorem is. This is our conditional statement from before. So we haven't changed what we've been doing. Only the left versus right is changing. And because we're looking for the left side given the right side, the denominator is what's the uglier part about this. Okay, you take that to your calculator. Make sure you're really careful about it. So I ended up in the numerator taking that as 15/60. I did a misfraction. So this would be 1/20 plus 15/60. You cannot do any canceling top to bottom because things are separated by plus signs. So don't try and do that. And then this is what? 3/12. Then you can go to your calculator and just add them. Make sure that you get the entire denominator instead of parentheses. And what you should end up with is 5/11, which comes out to be 0.455. So 0.455. Okay, let's try another example. Now that we've seen the theorem and we kind of understand what we're doing, let's do some examples. So example 3 says a card is drawn from a standard 52 card deck, and then a second card is drawn without replacing the first. If we know that the second card is a spade, what's the probability that the first card is a spade? Okay, so we're looking for the probability that the first is a spade given the second is a spade. Let's organize our information. So we're going to make a tree, and what we're caring about this time are spades or not spades. So here's a spade, spade complement, and this is the first card. And then on the second card, it's a spade or it's not a spade. And again, remember, this is without replacement. So we're going to hold on to our card as we get the second card. Okay, so there are 13 spades in the deck out of 52. That means the other 39 cards are not spades. Okay, I have a spade in my hand, so I'm following the first branching. That means there are only 12 out of 51 spades left in the deck, but because I have a spade in my hand, the other 39 cards are not spades, and these two together will add to 51 over 51. Okay, I have a non-spade in my hand. That means there are 13 spades still in the deck out of 51. I have a non-spade, so there's only 38 not spades left in the deck. And again, those are going to add to 51 out of 51. Okay, so we're looking for the probability that the first is a spade given the second is a spade. So your clue is that we're looking for the left given the right. That means I cannot just pick the answer off. If I were looking for the right side given the left side, I could just pull the answer off, but I can't. So we have to go through the theorem. So we need the branching that does first spade and second spade. So that's my top branching. So that's 13 out of 52 times 12 out of 51. All over every branching that ends with a spade. So that would be the same repeated one plus this one down here also. So we're going to have 13 out of 52 times 12 out of 51. Plus, we'll take 39 out of 52 times 13 out of 51. And you'll notice you have a common denominator, so you can actually work the fractions fairly easily if you want to do it that way. You're more than welcome to. And once you're done with all the arithmetic and all the cleanup, I ended up with 0.235. So the probability that the first card is a spade given the second card is a spade is 0.235.